Hello everyone, Mrs. Hanson here to begin a next new chapter with you, taking a next step in our lessons in our chemistry class, looking at energy changes, reaction rates, and equilibrium in our Chapter 6 topic. You have printed out your notepad and are ready to start with me, looking at the topics as follows. I'd like to talk about energy and how energy plays a role during chemical change. We'll talk about things such as endothermic and exothermic reactions, and we'll display those reactions on what we call energy diagrams. The next thing we'll look at are the kinetics, the rate of a chemical reaction. Just because a reaction is spontaneous means that it occurs naturally. We don't really get an idea about how fast it occurs until we discuss reaction rates. And then, to wrap up our last topics in our chapter, equilibrium and Le Chatelier's principle, which means to upset the equilibrium and watch it reestablish. Keep in mind there are some assigned readings in this chapter as well. You'll look at the focus on the human body in the last section, body temperature, and then you'll also have some assigned reading back in reaction rates, and those are in your notepad clearly labeled for you as well. So be sure to spend some time with your book kind of pulling out information to fill out that part of your notepad. Our learning goals, we'd like to define energy and become familiar with the units of energy. What is a calorie? What is a joule of energy? We'll use what we call bond dissociation energies to predict bond strength. Reactants break bonds, products form new bonds. How much energy is associated with each one of those actions? And that truly is the heart of chemistry. We'll describe energy changes in a reaction to classify them as endothermic and exothermic and represent those on what we call energy diagrams. So we'll be drawing a little bit of enthalpy in terms of heat of reaction. How does changing the concentration, the temperature, and the presence of a catalyst all affect the rate of a reaction? And we'll describe the basic features of chemical equilibrium, looking at a forward reaction and a reverse reaction that are in dynamic equilibrium. Le Chatelier's principle will allow us to predict what happens when equilibrium is disturbed. And if we do put a disturbance on a reaction that's in equilibrium, we'll apply Le Chatelier to predict if the forward or the reverse reaction will be favored. All kinds of good stuff related to chemical equilibrium. So remember, why are we studying this? What is it about energy and reaction rates that devotes our time? Well, remember, some reactions, such as like combustion of fossil fuels that makes our cars move, for instance, even the metabolism of carbohydrates when you eat sugars or proteins or fats, they release a great deal of useful energy. Why is that? Why do other reactions absorb energy from the environment? Some reactions occur very quickly, others do not. This chapter just allows us to explore energy changes observed when bonds break and new bonds form. So the heart of our chapter, all about energy and how it applies to a reaction. So we'll begin by simply defining the term energy. And in your notepad at the top it says, what is energy? And I'd like you to simply write energy, a classical definition here, is the capacity to do work. Energy comes in two different forms. If energy is the capacity to do work, we look at two classes of energy, what we call potential energy and what we call kinetic energy. I'd like you to define potential energy as the energy that is stored. The energy of position is another way to define that. Now in chemistry, potential energy is that energy that's stored within a chemical bond. And when we break bonds, and that's what chemistry is all about, energy is released. A second category is known as kinetic energy. And I'd like you to define that as saying it's the energy of motion. Anything moving possesses kinetic energy. We call this the law of conservation of energy, which is a law in thermodynamics. It simply states we cannot change the amount of energy in the universe. We cannot create it. We cannot destroy it. All we can do is let it change from one form to another. The law of conservation of energy says the total energy in a system does not change. Energy is conserved. Energy can change from one form to another. But the amount of the energy in the universe is constant. So a great example of potential energy, and I know this is archery, which is coming up in the Summer Olympics, pulling back that arrow, pulling back the string on the bow and having the arrow ready to launch. When that position is as far back as that lady can possibly pull, she's got potential energy stored in that bow. And of course, when she releases that, you have that now in motion, all of this stored energy in this particular, the string being pulled back is then released and the arrow goes forward. So stored or position, and then of course the motion creates kinetic energy. And I like this diagram too. Here we are at the very top of a roller coaster hill. So 100% is stored energy, the energy of position, gravitational energy here. And then of course you start to go down the hill. About halfway, you have half kinetic energy, half potential energy. And at the very bottom of the hill, 100% kinetic energy because there's no energy of position any longer. So at the top of the hill, stored energy, and when you're in motion, kinetic energy. And when you think about this law of thermodynamics saying we cannot create nor destroy the amount of energy in the universe, we only allow it to change from one form to another. These are examples of those types of energy. Potential energy in chemistry is the energy stored in bonds. Kinetic energy in chemistry is thermal energy, the energy of moving particles, such as heat flow from a hot object to a cold object. There are other types of potential energy, such as elastic. Remember that bow that we talked about in the previous slide? When she pulled back the string, she was storing energy due to tension. There's other types, such as nuclear. You blast apart a nucleus of an atom, all kinds of energy is released. Or gravitational potential energy, like at the top of the hill in the roller coaster. Kinetic energy includes thermal, mechanical, electrical, sound, and electromagnetic waves. All of those on the EM stands for electromagnetic spectrum. All of those are in motion. So if we're studying energy, specifically in chemistry, it will be stored in bonds or released or absorbed as heat. So our focus, of course, is chemical bonds. Chemical bonds store potential energy. And a compound with lower potential energy is more stable than a compound with higher potential energy. That is just really a natural law. It says compounds want to be at the lowest energy possible. And I think about the natural state. I think all of us want to be at the lowest energy level possible, especially with our 8 a.m. chemistry class. Then we see that reactions that form products having lower potential energy than reactants, they're actually favored. So what that means just visually, here's energy on and just kind of draw this with me, if you will, in your margin. Here we have just an XY axis where we can see on the Y axis is energy. And we'll learn that energy is going to be measured in joules or in calories. Calories might be a more familiar term just from food intake is measured in calories. And in the metric system, we'll write down joules. But you can see as energy is increasing on the y-axis, and you can just think of this as time. Time goes by and reactants turn to products. You call that progress of a reaction. If the reactants have this, just kind of an arbitrary line that I draw, a starting amount of energy, and we'll learn that there's this little energy barrier that separates reactants and products. We'll learn that this is called activation energy. And again, we'll redraw this several times because we'll have this energy barrier that here I'm going to abbreviate EA as the activation energy. And as time goes by, the reactants turn to products. And you can see then there's a difference in the amount of heat content, the amount of energy between the reactants and products. The reactants are of higher energy than the products are down here. And we'll see that heat is released. And this is a more stable configuration because they are of lower products. We will learn that this will be called exothermic, heat releasing. And when bonds break and new bonds form, heat is being released, energy is being released, and we'll measure that energy using bond dissociations. So these units of energy I've been saying, one is known as a calorie, and you can abbreviate that with a small c, or some people will write out CAL for calorie. We define that to be the amount of energy needed to raise the temperature of 1 gram of water by 1 degree Celsius. So a small case calorie, how much energy needed to raise 1 gram of water, 1 degree Celsius. That is also known as the specific heat of water. And you should know that the specific heat we'll learn is a kind of a definition for this. And it just says the specific heat of water, you can say, is 1 calorie. It takes 1 calorie to raise 1 gram of water by 1 Celsius degree. And so in the metric system, there is another unit of energy. Now in America, we're used to the English system carrying calories of energy, but we should also be familiar with the metric system. The unit of heat energy is known as the joule. And this is actually an honorary name from a physicist whose last name was Joule. So you'll see that was a capital J when we write out its unit. A joule is another unit of energy. So you could say the specific heat of water in a joule is 4.184. That's the conversion between a calorie and a joule. It takes 4.184 joules of heat energy to raise 1 gram of water by 1 Celsius degree. The equivalent values between calories and joules should be memorized. You'll need to know those conversions, so I'll just encourage you to remember 1 calorie is equivalent to 4.184 joules. So both joules and calories can be reported in larger units. So these are actually kind of small calibrations. When I say 1 calorie, it's kind of a small number. So joules and calories are more often reported out in kJs, kilojoules, and kilocalories, kcals. So just thinking that through, we know that kilo means 1,000. So it takes 1,000 joules to equate to 1 kilojoule. It takes 1,000 calories to equate to 1 kcal, a kilocalorie. And so we can equate these two as well. A kilojoule and a kilocalorie would have the same conversion as a calorie to joule. 1 kcal is equivalent to 4.18 kilojoules, kJs. So let's kind of bring that out to practice. Let's practice converting between heat units. You'll need a calculator for this part of your lesson. Perhaps pause your video if you've not yet grabbed your calculator, or perhaps you're used to having a calculator every time we start with chemistry. But this is the bottom of page 1 where it says, let's practice converting between heat units. And I pulled this right out of your text. A reaction releases 421 kJs of energy. How many kilocalories does this correspond to? So we're working to memorize our conversion that we equate 4.184 kilojoules is the same as saying 1 kilocalorie. So let's begin by writing what was given to us, 421 kJs. Now remember, our conversion What is it that we want over given so that our unit will cancel? We were given a kilojoule. I want to make sure it cancels, so it must go on the bottom. And I want to end with a kilocalorie, so it needs to go on the top. So we end with it. Our conversion says 1 kilocalorie is equivalent to 4.184 kilojoules. So this looks like a divide by problem. And let me pull my calculator out. Let's hit this together. I have 421 divided by 4.184. And my screen reads 100.621 and it goes on and on and on. Let's consider sig figs. I have 3 sig figs here. So my answer should also have 3 sig figs. So I'll round to 101 kilocalories. That's not too bad, is it? Let me ask you to try some on your own. Please pause the video, work to create mastery, right? So the more you practice on your own, the more proficient you become. You're turning the page in your notepad to the top of page 2. Come back to the video when you're ready to check your answers. Pause, work ahead, and then come back. That's me turning the page. In letter A, we started with 42 joules, and we wanted to go to calories. Remember what we want over given for our conversion. We want to switch to calories, and we were given a joule. We know that our equivalent values, 4.184 joules, is the same as saying 1 calorie. So you divided. You said 42 divided by 4.184. And you found 10, and your screen said 10.038. But remember, we're considering sig figs, so I'm going to write 10 with a decimal point to make sure that's 2 sig figs, and my unit there is calories. 55.6 kcals to calories. So what is it that we want? We want a calorie given a kcal down below. Whoops. So I think about want over given. It takes 1,000 calories to equate to 1 kcal. So we're moving our decimal place 3 spots over. So when I write that out, 55600. Now I think about sig figs. This is the number of calories. I'm only allowed 3 sig figs in my final answer, and right now I have ambiguous zeros. So if I don't leave as, no decimal point, because I don't want those zeros to be significant, I'll still have only 3 sig figs. So 55600 with no decimal point gives me the correct magnitude of the number and still 3 sig figs. I did place a decimal point here to ensure I had 2 sig figs, so that one was needed. I'm kind of reviewing our sig fig rules. 326 kcals to kjoules. So here I want my kilojoule and I need to cancel the kcals. 4.184 is our conversion between the land of kilocalories to kilojoules. So 326 times 4.184, and we get a value that says 1363.984. We need 3 sig figs. So this fourth number here is looked at, and it is not up high enough to round. So 1360. That's 3 sig figs with no decimal, kilojoules. Letter D. 25.6 kcals times, let's see, we want joules. I need to go, so this is a good one. We need actually 2 conversions, don't we? Because our conversion says a kcal to a kj, I can get there. And so I have to give myself a little more room. So let me just rewrite that answer. Yeah, this will work for us. We want kcals. And so therefore, to cancel kcals, it takes 1 and 4.184 kJs. And I can easily convert from a kj to a j. And by doing that, we know it takes 1,000 joules to equate to a kilojoule. So this involved two transfers. Kcals canceled in the first step, kjs canceled in the next step, and we'll finally land to joules. So to hit that, 25.6 times 4.184 times 1,000. And my screen has a really big number. It says 107,110.4 joules. We have to equate that to 3 sig figs. There's 3 there. So 3 sig figs, 107,000, no decimal. And that way I'll have 3 sig figs in my final answer. So I have the correct magnitude, the size of the number is correct, and I have 3 sig figs reported. Good work. There's some more. A combustion of gasoline releases 11.5 kcals of energy. So that's the number of kilocalories for every gram of the gasoline that's burned. How many kilojoules of energy are released? How many joules does this correspond to? So the 1 gram is telling us the amount of energy, but it really doesn't play a role in the calculation. It's giving us kcals of energy, and we want to know kilojoules. So we can use our conversion where we know 1 kcal is equivalent to 4.184 kJs. And we can get our first part of the answer by simply multiplying 11.5 times 4.184. Did you find 48.116? And then we'll consider proper use of sig figs, so we'll round 48.1 to get 3 sig figs, and that's a kj. How many joules does this correspond to? Well, that's just changing out our kilojoules into just simply a joule. And we know kilo means 1,000. So there's 1,000 kilojoules or 1,000 joules in 1 kj. That means we're going to take our decimal and move it 3 spots to the right. So that becomes 48100 joules. No decimal point, so I can retain 3 sig figs. How are you doing? These aren't bad at all, especially after coming off of stoichiometry. I'm sure these are nice. Now, where can we apply this? And we'd like to talk a little bit about energy and nutrition at this point, kind of bringing in an application of, these units called calories and joules. When we eat things that contain proteins, carbohydrates, and lipids, we're actually metabolizing those large molecules into simpler molecules. And when I say metabolize, that just means we're breaking down, right? This is a decomposition type of process. And we're breaking them down into simpler molecules that release energy. Releasing energy because bonds are breaking. So we eat complex molecules, digest them, and release the energy stored within those chemical bonds, and our cells capture that energy. Maybe you've heard of the type of energy cells use, known as ATP, for just cell maintenance and cell growth. Now, what's interesting, when you read a food label and you're looking at calories, 200 calories from fat, from 10 right here, notice that this is a capital C, calorie with a capital C. That nutritional calorie is the same as saying a kcal that we were just calculating. So 1,000 calories is the same as a capital calorie. When you write CAL with a capital letter, keep in mind that's a nutritional calorie, and it's 1,000 calories. So this equivalency, 1 kcal, is the same as a capital calorie on a nutritional label. Now, every gram of protein you eat releases 4 calories, 4 kcals, if you will. Every sugar that you eat, 4 kcals. So these are equivalent nutritional values. And look at the fats or the lipids that you eat, releases 9 nutritional calorie units for every gram that you eat. So we have a 4, 4, and 9 value to remember. We can apply that into some sample problems where we calculate nutritional calories. Let's say we eat a baked potato and it has 3 grams of protein. It has 23 grams, oh, it has a trace of fat. I like that. Trace of fat, not even enough to calculate, and 23 grams of carbohydrates. Estimate the number of food calories that you ingested by eating the baked potato. So again, from our conversion where I said, remember these conversions, it allows you to solve problems like these. I remember that we have 1, if you go back to this conversion, just make sure you see that. For every 1 gram of protein, 4 calories of heat is released. Carbohydrates, same number, 4 calories for every gram that you eat. So notice we have grams, so we're placing up here 4 calories. Notice I'm writing a capital C for every 1 gram. And it's the same for the carbohydrate. There are 4 capital C calories in every 1 gram of carbohydrates as well. So 3 times 4, that I can do in my head, that's 12 calories of energy being released from the 3 grams of protein, but I have to hit on my calculator. For 23 times 4, that's 92 calories of heat being released for ingesting the carbohydrates. And so the total calories in my baked potato is 92 plus 12, and that gives me 104 nutritional calories. And so I write that with a capital C. About 100 calories to eat a baked potato. Not too bad. Shall we try another? How many calories are contained in a tablespoon of olive oil, which contains 14 grams of fat? Okay, so here, 14 grams of fat, which is lipids in our biomolecules. Now I have to remember that 9 calories of energy are released in every 1 gram of fat. So now my conversion says there's a lot more stored energy in a fat molecule than in sugars and proteins. So 14 times 9 gives me 126 food calories in that tablespoon of olive oil. Why don't you try the next one? Looks like a very tasty cheeseburger. How many calories are in that cheeseburger? Pause your video and just take a moment to calculate. How many calories, by reading through this problem, come back when you're ready to check your work. Knowing the number of grams of protein, carbs, and fats allows you to estimate the food calories of any food product. So here's a 1/4 pounder with cheese. We have 29 grams of protein. Each gram will release 4 food calories. We have 40 grams of carbohydrates. And in that would also release 4 calories for every 1 gram. And there's 26 grams of fat. And that's going to release 9 calories for every 1 gram. Let's go through and find each individual's contribution to the total. 29 times 4. So from proteins, we're getting 116 calories. 40 times 4 gives us 160, the contribution from the carbs. And 26 times 9 gives us 234 calories from the fat. So the total is that sum, 116 added to 160 added to 234. There's 510 calories in our cheeseburger. Still looks delicious, don't you think? So in our first lesson, we've practiced with identifying types of energy, kinetic energy and potential energy, knowing that in chemistry, our focus is on stored energy in bonds and breaking it to release heat or forming them to absorb heat. Molecules move, they have kinetic energy. And as we consider energy changes in reactions, we think about, what is chemistry? How do these molecules come together and reactants go to form products? Well, the heart of that answer is understanding when molecules come together and react, there's a collision. And so when I say a collision, you have to think about literally two molecules that are in motion must collide with one another to break bonds, or they must come into contact with each other to form new bonds. And that's the heart of a chemical change. Bonds are broken in the reactants, and new bonds are forming in the products. To break a bond requires energy. So think about this as part of your example. Energy is required to break this bond. And when we break a bond, each electron that's in the shared pair returns to its original owner. So we end up with 2 atoms of chlorine. So we have a Lewis dot structure of a diatomic molecule, a chlorine to a chlorine, a shared pair. When we're drawing our Lewis dots, we represent all electrons around the chlorine. And then we're breaking a bond in this arrow. And now we go back to 2 atomic chlorine atoms, which of course live in group 7A. So we see 7 dots representing the atom. To break the bond actually required 58 kcals for every mole. So when I wrote energy here, I could even include the number 58 kcals to break a whole mole's worth of chlorine molecules. To cleave means to break. To break the bond requires energy. And now just flip that around. Let's put it back together. So here we're breaking bonds, here we're forming bonds. To form a bond releases energy. Releasing energy means the energy that it takes to store that, putting it back together, is now released. So I'm going to just put that over on this side to remind us that 58 kcals of energy is released on this side of the arrow, and it's going to be absorbed on this side of the arrow. We will learn that if energy is required to make a reaction occur, we call that endothermic. And if energy is released through a chemical change, we'll learn to call that exothermic, heat releasing. And here it would be heat absorbing. And I really like placing these on the left side of the arrow for endothermic. The heat is required, so you put it on the reaction side. And if heat is being released over here in the exothermic, I put it on the product side. It's just coming out of the reaction. And notice they are exactly the same amount. If 58 kcals is required to break the bond in the forward direction, you would have 58 kcals coming out of the reaction in the reverse order. So we've said some important words, endothermic and exothermic reactions. What we're really looking at is something known as bond dissociation energy. To dissociate means to separate or break. How much energy is needed to break bonds or to separate the atoms into their own individual components? And this delta H is going to be the symbol used to represent the heat of a reaction. It's known in thermodynamics as an enthalpy change. The heat of a reaction. If heat is released, we called it exothermic. If heat is absorbed, we called it endothermic. The enthalpy change is the heat content through the course of a chemical reaction. Remember, to break bonds, it requires energy. That was an endothermic process. Notice that it has a positive sign for the kcals per mole. Endothermic, delta H, will always be positive. Because it requires energy. Think of it as a reactant on the left side of your arrow. It's required. You have to input energy to make the reaction occur. And notice this is just pointing to the breaking of the bond. To break the bond requires energy. Now, opposite of that, to form the bond releases energy. Delta H will always be negative. And that's true every time you have an exothermic reaction. The heat of reaction is releasing energy. To release energy, think of it as a product on the right side of the arrow. It's coming out of the reaction. So the word enthalpy change, enthalpy is really just nothing more than heat. It's a thermodynamic property in chemistry. Perhaps if you had a high school chemistry, you learned about enthalpy. Perhaps you even heard about entropy, which is disorder, and these are just thermodynamic properties. Delta H, enthalpy, delta S is entropy. We're looking at enthalpy, a thermodynamic process. Just think of it as heat. How much heat is associated during a chemical change? If it's being absorbed, endothermic. If it's being released, exothermic. The bond dissociation energy, to define the term. Let's write that as saying it's the heat, the delta H is heat, for breaking a covalent bond between two atoms. The bond dissociation energy. How much energy does it take to break a bond? There, perfect. The amount of energy needed to break a bond is known as bond dissociation energy. And remember, to break a bond is always an endothermic process, so it will always be a positive number. Notice that an endothermic process is always a positive number. So to break a bond, which is the term cleave, to cleave a bond, each of the atoms receives one electron, right? So I'm breaking this, the two electrons that are in the shared pair cut right down the middle, and we form atoms. So we had a molecule of hydrogen go back to two separate atoms. To do that required 104 kcals of energy. Now the opposite process, to put it back together, to form a bond. Forming a bond releases energy. It's an exothermic value, so it's always a negative number. They're equal but opposite signs. Forming bonds releases energy. Breaking bonds requires energy. So as we think about bond dissociation energy, we can also consider a periodic trend. The stronger the bond, the higher its bond dissociation energy. It takes more energy to break stronger bonds. Now let's put that together with a periodic trend. Let's consider the halogens, group 7A. And if you can just envision your periodic table, at the top of group 7A is fluorine, underneath that is chlorine, underneath that is bromine, underneath that is iodine. So there are the halogens as we refer to them. Now, if we consider just a bond between HF, HCl, HBr, and HI, and that's what we're showing here, those bonds between the halogens. The strongest bond is between the smallest atom. Fluorine is smaller than chlorine. Chlorine is smaller than bromine, and iodine is the biggest of all. So what that means is that this bond is the strongest because the fluorine's protons are holding tight to the electrons. It is the most electronegative element. In terms of electronegativity, fluorine is holding these electrons very, very tight. A tight hold on electrons. And then as you think about, the size of fluorine, here's its nucleus, and it only has 2 energy levels. And so you can see that the protons have a great ability to keep its electrons close. By the time you get to a chlorine, there's 3 shells on the chlorine, so this has become a little more shielded. The protons are having a harder time keeping those electrons close. And by the time you get out here to iodine, you have 5 valence shells, and the protons are very shielded by those outer electrons. And so therefore, this bond between HI is not as tight and it's easier to break. The smaller the atom, the more electronegative the atom, the stronger the bond. The bigger the atom, the least electronegative atom is the weaker bond. And you can see based on the bond dissociation energies, HF requires 136 kcals per mole to break that bond. HCl requires a little less, 103 kcals per mole. HBr, a little bit less yet, 88 kcals per mole. And the HI is at 71 kcals per mole. You will see the bond dissociation energy decreasing as you go down the column. This would be the highest bond dissociation energy, and this would be the lowest bond dissociation energy. Bond dissociation increases as you go up, or you could say it decreases as you go down, however you want to refer to that. But the reason is because atoms that are small are more electronegative, holding the atoms tight together in a very tight bond. By the time the atoms get really, really, really big, the bonds are not held as tight, and that's a weaker bond. Less energy is required to break a weaker bond. And here you have a bond dissociation energy chart. And I just clipped this from your actual textbook, and you place that right into your notepad as well. So you have this to kind of look at as you solve problems. You can see the values here. These are breaking bonds. Bond dissociations mean to break bonds. And I know they're breaking because all of these are positive values, right? To break a bond means it's a positive value. To break bonds is dissociation. To form bonds is what we call bond formation. So let's practice just reading this chart with this example problem here. It says, write the equation for the formation of HCl from H and Cl atoms. So it's just saying, here's an H, here's a Cl, and it comes together to make HCl. This is a hydrogen atom. This is a chlorine atom, and this is a hydrogen chloride molecule. That's all it's really telling us. Now, did we form a bond or break a bond? Well, clearly we see a formation of a bond. So delta H is going to be negative because we made a bond. And I know exothermic is always negative. Well, how much energy did it release? When I find my value, and it's just really reading this chart, here's the HCl, I read across, and notice it's positive because that's a bond dissociation energy chart. Bond dissociation is endothermic, but we're just going to flip the answer to be negative 103 kcals per mole. That means it's being released, so you can think of it on the product side. It's exothermic. That was easy. It took 103 kilojoules of energy to form the bond, or to break the bond, to dissociate the bond is endothermic. These are all bond dissociations. Since we formed a bond, forming bonds is exothermic. Why don't you try some? You still have your chart in front of you. Remember, give the delta H for each reaction and classify as endo or exothermic. Come back to the video when ready to check. Well, let's find letter A. Letter A is breaking a bond. When bonds break, we know that it dissociates. To dissociate means to break. We want to get those words kind of the same. To dissociate is to separate. Think of dissociate as another way of saying separate. You're going to break this bond. So HBr, when I come to my chart and I just find HBr and I just read across, and I would notice that the value there is plus 88 kcals per mole. So for letter A, the delta H is positive 88 kcals per mole, which makes this an endothermic process, meaning that it takes energy. Energy is absorbed by endothermic. How about letter B? Well, letter B is forming a bond. And to form a bond, we know is exothermic. So let's go to our bond dissociation chart and find HF. And of course, I see it right here. So with HF, the delta H is given as positive 136 for breaking, but we're forming a bond in letter B, so we know it's going to be negative 136 kcals per mole. That is an exothermic process, meaning that heat is being released from the system to the surroundings. And letter C, HOH, we're breaking a hydrogen to oxygen bond. Breaking bonds is endothermic. So where did you find that on your chart? Oh, it's right above here. So it's 119. So delta H is 119. Now remember, we're breaking bonds, so it remains positive. We know that it is exothermic and that heat is being released. That's why you have, oh, that's bad. Heat is being absorbed. I'm so sorry. I just fixed that quickly. Heat is being absorbed in an endothermic process. I'm glad I caught that and didn't live forever with that mistake. I'll make a smiley face so you know I goofed, but I corrected it. A positive value is endothermic. Heat is being absorbed every time we dissociate a bond, means to break it, we absorb heat energy. So breaking bonds, you know it's a positive value. Forming bonds, you know it's a negative value. That is correct. Let's try to digest this one. We have to turn our page a little bit here and come up with a next question. Let me model one with you here. Which of those indicated bonds would have a higher bond dissociation energy and why? Well, as I look at the trend, I'm investigating a carbon to fluorine bond, and here I have a carbon to chlorine bond. Those are both halogens. You remember the halogen column, fluorine, then chlorine, then bromine, then iodine. This is group 7A, known as the halogens. And I remember saying that bond dissociation energy increases as you go up a column, that a carbon to fluorine bond is stronger than a carbon to chlorine bond. This is a stronger bond because fluorine is smaller, making it more electronegative. So which one has a higher bond dissociation energy? The CF. And our reason? Well, because fluorine is a smaller atom than chlorine, making it more electronegative. So ultimately your answer is, well, that's the stronger bond. It's higher up as a smaller atom. How about you try these two? Pause the video and just ask yourself, which one is the stronger bond and why? All right. Well, here I bet that's very similar to what you just practiced. Here I have a Ci or a CBr. And clearly you can see, as you remember your halogen trend, fluorine, chlorine, bromine, iodine. The stronger bonds increase as you go up the column. So who's higher up? Well, of course, it's bromine. So this is the stronger bond. Bromine is more electronegative than iodine. It's a smaller atom, therefore it's a stronger bond. That means it has a higher bond dissociation energy. Can I write BDE, bond dissociation energy? What'd you do with letter B? Well, this is a trend from group 6A. That's oxygen's family. Oxygen is above sulfur on the periodic table. So remember the trend, as you go up a column, bonds get stronger because atoms are getting smaller. So therefore, this is the stronger bond. Because oxygen is smaller, it's more electronegative. It has a tighter hold on those electrons. So it would have a higher bond dissociation energy, being that it's a smaller, more electronegative bond, it's a stronger bond. Okay, we're doing great. We can actually bring in some of these calculations into a delta H value, writing thermochemical equations. So I think about this thermochemical equation is just more or less the same thing as a balanced chemical equation with the delta H information included. So think about that, and we'll write out one for methane. So on your paper, we're writing CH4, that's our methane molecule, plus 2 moles of oxygen. These are all in the gaseous phase, forming a mole of carbon dioxide gas and 2 moles of water. And as part of that, you're going to write delta H is negative 213 kcals per mole. You're just including the delta H value right at the end of your chemical sentence. Now I want you to notice the negative sign. Negative sign means heat releasing. It's exothermic. Exothermic reactions release energy from the system to the surroundings. Exothermic. Well, this is actually an endothermic graph. The exothermic graph, if I may, just compare the two quickly. Let's do a compare and contrast. In an exothermic, we have the reactants of higher energy than the products. And that's what this reaction would show, exothermic. we would have the reactants and the products separated by an energy hill. We'll learn to label that as the activation energy. When we see a diagram that shows the reactants of higher energy than the products, this is our value here of delta H, the heat of reaction. And notice that if delta H is negative, that's an exothermic process. And that means the reactants released energy. And we would just say in this example, as I read that amount, 213, on our graph, that would be 213 kcals difference between the products and the reactants. The reactants let off 213 kcals of energy. And the reason I redrew that is, notice here, I have a graph where I have reactants climbing this energy barrier called the activation energy, and the products actually ended at a higher state. Well, this is an endothermic process, meaning that energy is absorbed and it's required. So the activation energy, again, from the point where you see the reactants up to the very top of the hill, that's called the activation energy. How much energy is needed to start the equation? Since the products are of higher energy than the reactants, the delta H here, the heat of the reaction, comes out positive. So we'll compare those graphs in an exo and endothermic process. Drawing the energy diagram for methane is this requirement. Methane released 213 kcals of energy. Now if we consider this reaction, where carbon dioxide and water form glucose and oxygen. This is the thermochemical equation for photosynthesis. 6 moles of carbon dioxide in the gaseous form plus 6 moles of water in a liquid form react to form 1 molecule of glucose, C6H12O6, and 6 molecules of oxygen. The thermochemical equation includes the delta H at the end of your chemical sentence. So thermochemical equation says, write out your balanced chemical equation, and at the end of your sentence, include the information about delta H. Now notice this is a positive sign, meaning that it's heat absorbing. And if I'm absorbing energy, it's an endothermic process. And this is the graph that we'll draw for an endothermic process. And this is actually correct. The reactants climb an energy barrier and end at a higher amount of energy than the initial reactants. So reactants go to products. I'll just write R and P. You can do the same. With its energy diagram, we're learning the activation energy is the amount of energy needed to go across this little energy barrier. I'm going to abbreviate that as EA, the activation energy. And down here, the difference between the reactants and the products is your heat of reaction. And since we're at a higher value, positive 678 kcals should be labeled on your graph. So as reactants climbed to products, it had to absorb 678 kcals per mole. So we're just looking at energy changes, heat releasing, heat absorbing, kind of sprinkling in actually the next section as well, talking about energy diagrams. If you see the reactants of lower energy as compared to the products, it is endothermic. If you see, as in what we drew here, the reactants of higher energy as compared to the products, that's how we know it was exothermic. Our energy diagrams compare the amount of energy stored in the bonds of the reactants as compared to the products. Let's consider this. When 2 molecules of ammonia, NH3, decompose. This is a decomposition problem. It decomposes to form 3 molecules of hydrogen and 1 molecule of nitrogen. To do so, the delta H is included as 22 kcals per mole, and notice its sign is positive. This is a thermochemical equation. It's a balanced chemical equation that includes the delta H information. I want you to think, and the true definition of this is enthalpy, which is a thermodynamic property related to heat. But it's really okay to just think of delta H as the heat. How much heat is being absorbed or released during this reaction? Well, from a thermochemical equation, to know if it's being absorbed or released, we simply look at the sign. The sign on delta H we see is positive. So a positive delta H indicates that it is an endothermic reaction, meaning heat is being absorbed. It is required for the reaction to occur. Requiring energy means that the reactants are stronger bonds than the products. So all endothermic reactions, the reactants have stronger bonds than the products. And the opposite would be true, right? If it were exothermic, the products would have stronger bonds, heat releasing. So if you think about this energy diagram, I would have the reactants down low and the products up high. The reactants turn to products. And just think about, here's our energy on the y-axis, and just saying as energy goes up, the difference between the reactants and products is known as your delta H. And this would need to absorb 22 kcals of energy for every mole of reactant. So there's your visual of an endothermic reaction, absorbing energy. So clearly you see the reactants are of lower energy. The reactants are. In that graph, just to emphasize, reactants absorb to go to products. The reactants are here of lower energy. The products are up here, so therefore they're of higher energy. And this is an endothermic process. Heat is being absorbed. Digest that, huh? How about trying this one on your own? Well, this is going to involve a little calculation. So, well, let's try this together. I'm not going to ask you to try it on your own unless you want to pause and just kind of process, take a little break, but I'll go ahead and kind of model the first one. We're looking at a thermochemical equation. And I know that the thermochemical equation is just a balanced chemical equation that includes the heat of reaction. And that is going to allow us to see that this is an exothermic process. And just to think about that, we have an exothermic, meaning the reactants go to products where the heat is being released. So as reactants turn to products, our delta H, the difference between the energy level of reactants to products, is negative 531 kJs. We'll also learn to define this area as the activation energy, E sub A, how much energy is needed to separate the reactants and products. But the delta H is the difference between the reactants and products. And we'll practice that in our section 3. I'm just seeding that so it's easier when we get there. The combustion of propane, C3H8, with oxygen occurs with the balanced chemical equation, and it releases 531 kcals of energy. How many kilocalories of energy are released when 0.75 moles of propane are burned? Well, this is a conversion. So this is our given amount. We have 0.750 moles of propane. And this is just a conversion of we've been practicing what do we want from given. Well, we want to solve for kilocalories given the number of moles of propane. Given a mole, calculate a kilocalorie of energy. From your balanced equation, we have negative 531 kcals. See how that's just right here as part of your balanced equation? And the number in front of the propane here is 1. So this is what we would call our stoichiometric ratio. The little heart of our problem in the stoichiometric ratio, our want over given. We want to know kcals. From the balanced equation, it's negative 531. We were given moles of propane. From the balanced equation, its coefficient is 1. So let's go ahead and solve that. 0.75 times negative 531. And my screen reads, well, I'll write it down here, negative 398.25. Let's turn that into 3 sig figs, so negative 398 kcals of energy released. A one-step mole conversion, really, where we're inviting kcals into the stoichiometric ratio. Shall we try one more together? What if we're given 1 mole of molecular oxygen and we're asked to solve for kcals of energy? With this conversion, we want to know kcals given moles of oxygen. And just think about your want over given ratio from the balanced thermochemical equation. Those conversion factors just come from your equation, don't they? We want to know kcals. Its coefficient, or its value here, is negative 531 from the balanced equation. And we started with moles of oxygen. Its coefficient from the balanced equation is a 5. So our ratio, our want over given ratio, negative 531 kcals for every 5 moles of oxygen. And when you solve for that, 1 times 531 divided by 5. And my screen reads negative 106.2, but we should probably just carry the 3 sig figs, negative 106 kcals of energy. We just practiced doing mole conversions using balanced chemical equations. Now that I've modeled 2 of those problems, I'll encourage you to try the others on your own and come back to the video when you're ready to check. You have a few problems on the remainder of page 6. Welcome back. Let's check out our work. Using the given delta H and the balanced equation for the reaction of magnesium with water, how many kcals of energy are released when 4 grams of magnesium are used? We're given 4.00 grams of Mg. Now I know that coefficients stand for moles. So therefore, no matter what unit I'm given, my job is to get it to a mole. So in step 1 of our stoichiometry roadmap, we divide, let me write that correctly. You divide to head into the mole, and we're going to divide by molar mass to convert into a mole. So in my first conversion, I had to go and find the molar mass of a magnesium atom, and I report that as 24.3 grams. So just to remind myself, we divide to head into the mole, and our conversion factor is called molar mass. Then on our stoichiometry roadmap, we ratio. Our ratio is always want over given. We want to know kcals. This is an exothermic reaction. I see the negative sign, negative 83.9 kcals of energy. And I started at magnesium, whose coefficient is a 1. In our first step, we divided to convert to a mole. In the second step, we ratioed. And our last step here will just be to calculate to end at kcals. So we have 4 divided by 24.3 times negative 83.9. My screen reads negative 13.81. I'm going to use my 3 sig fig rule, so negative 13.8 kilocalories of energy. How'd you do? Shall we continue? You have 3 more to practice with the glucose. Let's write this equation. We have C6H12O6, and it made 2 molecules of ethanol and 2 molecules of carbon dioxide, and in doing so it released 16 kcals of energy. So this is our thermochemical equation. That's a balanced chemical equation that includes the delta H information, the heat of reaction. In letter A, we'd like to know kilocalories, starting with 6 moles of glucose. So your given quantity already in the mole, very nice. So really all we need on the stoichiometry roadmap is the second step, the ratio, our want over given stoichiometric ratio. So from the balanced equation, negative 16 kcals, starting with 1 mole of glucose. So your ratio here, your want over given ratio, kcals per mole. The coefficient of glucose happens to be a 1. So here I'll hit 16, no, it's not 16, 6 times negative 16, and I find negative 96 kcals. Does that match your paper? I bet it does. You're doing great work. How about letter B? You started with 1 mole of ethanol. That was your C2H6O, and we want to know kcals. We see that negative 16 kcals from our balanced equation. And now notice that we have a coefficient of 2 in front of the ethanol. So that means for 2 moles of C2H6O. So the ratio of want over given is negative 16 over 2. And when I solve for that, negative 8 kcals are released. How about letter C? I'm going to give myself more room. This is 20 grams of glucose. And we want to know kilocalories. So that means we have to get into the mole first. So step 1, we divide by molar mass. Then we can ratio. So I've got to go to work and find the molar mass of C6H12O6. I know carbon has a molar mass of 12, and I see 6 of them in the formula. Hydrogen has a molar mass of 1, and there's 12 of them in the formula. And oxygen has a molar mass of 16, and there's 6 of them in the formula. So I'm going to count 12 times 6 plus 12 plus 16 times 6, and you find a molar mass of this sugar molecule as 180 grams. Now we can set up our want over given ratio. From our balanced equation, oops, I scrolled too far down, it was negative 16 kcals. And what about that coefficient in front of the glucose? Oh, right here, it's a 1. So there's our ratio step Step 1, divide. Step 2, your ratio, and that will land us at the kcals of energy, and we know it will be an exothermic answer. 20 divided by the molar mass of 180 times negative 16. And this gives me negative 1.78. Now I'm going back and saying this is good, 2 sig figs. And letter B should actually have 2 sig figs, so I'll do 8.0. And in letter C, we should actually have 3 sig figs, so I'm good there. Just considering that. 8.0 kcals for letter B would be the accurate sig fig answer. We did it. We've checked our work. We've accomplished through page 6. In your next video lesson, we'll come back and talk about energy diagrams. But I'll be honest, because I'm sneaky, we've already talked a lot about energy diagrams by drawing endo and exothermic reactions. Take a break, come back to your next lesson when ready.